addition of complex numbers. And we can also multiply a scalar by a complex number. So you'll just apply the distributive property, multiply the scalar with the real part, and multiply the scalar to the imaginary part, and you'll also get a complex number. So basically, a complex number is just a vector. And just like a vector, we can represent this in a plane. For example, in a Cartesian plane, we call this the complex plane. So in the complex plane, you can represent every point here as a complex number. So the horizontal axis is the real part, or the real axis, and the vertical axis is called the imaginary axis. So every number here is a complex number. Now here, let me just... Okay, at this point, this is the real number 4. Okay, and then at this point, this is the real number I, and this is negative I. Okay, so everything here along this line is an imaginary number. Everything here along this line is a real number. And everything here along on this plane, any pointer is considered a complex number. Now, my question is, this is a not a philosophy. I just like to ask anyone from the participants, how would you classify 0? Is it real or imaginary? The number 0. Is it a real number or imaginary? Let me see the chat. You can chat your answer, the I or R. I for imaginary, R for real. How would you classify 0? Is it okay, R? Actually, it's both real and imaginary, since it's in the intersection of this. So 0 is considered both real and imaginary. So that's a special number in many ways. 0 is a special number in many ways. It's the only number that's considered that to be real and imaginary. And it's still complex, of course, because if it's real, it's complex. If it's imaginary, it's also a complex number. Okay, what we can represent a complex number by for example, an arrow here, geometrically. So that for example, this is negative 2 plus 3i. So for the real part, negative 2, and the imaginary part. So there are two components. You have the real components and the imaginary components. Just like an ordered pair in a Cartesian coordinate system, in the complex plane, you represent the first component as the real part, and the second component as the imaginary part. So this is the representation of the complex number negative 2 plus 3i. Okay, since this is a vector, yesterday I discussed one of the properties of a vector, like the norm or the magnitude of a vector. In this case, we can get the absolute value of a complex number. So this is one of the important property. One of the important properties of complex numbers, their absolute value. Okay, the term absolute value. We're already taught about the absolute value in the real sense, right? Of real numbers, right? It's just, for example, the absolute value of negative 5 is 5. The absolute value of 100 is still 100. But the absolute value in a complex number is a generalization of that absolute value concept in the real world. Actually, the computation of the absolute value is you have to square the real part plus you have to square the imaginary part and take the square root, just like what we did with vectors yesterday. So that's the concept of absolute value. How is that possible? For example, if we have a real number 5, okay, that's just going to be 5 squared plus 0 squared, since your imaginary part is 0. And then you take the square root. Or negative 6, for example, negative 6 squared plus 0 squared, since your imaginary part is 0. So basically, this is the concept of modulus, or absolute value in complex number, is the generalization of what we understood as the absolute value in real numbers. Okay, and yeah, for this is the Cartesian form of the complex number. Z is equals to a plus bi. A and b is the coordinate. And these are some more examples of representing complex numbers. Addition. So basically, when we do addition with vectors, I'm not sure if I discussed this yesterday, but when we do addition of vectors, we use the tip to tail. We connect the tip to the tail and then project another arrow from the origin to get the final sum. For example, in this case, this is your vector W and this is your vector V, or this is your one complex number, another complex number. When you add them together, geometrically, what you're doing is you're just continuing the tip of the first arrow with the tail of the next arrow, and then you get the length from the origin to the tip of the second complex number. So the same thing, since complex number is can be considered as a vector. Complex conjugate. Graphically, we can represent complex conjugates as I mentioned a while ago. So it's easy to compute for the complex conjugate, but geometrically, we can see that a complex conjugate of a number, the conjugate of a complex number is just its mirror image across the real axis. Okay, it's just the mirror image across the real axis. That's the geometric interpretation of a complex conjugate. Absolute value or modulus, you can see in relation to the complex conjugate, it's actually the absolute value is just the product of the complex number and its conjugate. As you'll see, why is that? Because as you can see, a complex number z is a plus bi, right? Or in this case, uh, x plus iy. And then you multiply that with its conjugate, which is x minus iy. So plus, minus. So in your algebra, you have a difference of two squares. If you multiply those two binomials, okay, you just square the first one and square the other one, and then uh, get the difference. Okay, but as you can see, in the case of the imaginary part, your I will also be squared, and I squared is equals to -1. -1 times I, and since that it's minus, it will now become a plus sign. So that's why you get this. You have this one. Let me just illustrate that with a pen. Okay, to illustrate this example, you have x plus iy. Okay, if you multiply that with its conjugate, it's x minus iy. And the answer, this is as difference of two squares, just be x squared minus I squared y squared. But your I squared is equals to -1. So -1 times y squared. So it will now become this one, x squared plus y squared. Okay, so that's the relationship between the absolute value and the complex conjugate. So basically, when you get the absolute value, it's just the same as multiplying your complex number with its conjugate and getting the square root. In this case, for example, if you want to get the absolute value, 5 plus 6i, if it's in the Cartesian form, it's easy because you just have to get the real part and the imaginary part. You just square the real part, square the imaginary part, get the sum, take the square root. So the answer here is the square root of 61. So that's how you get the absolute value of a complex number or the modulus. Exercise. So what is the absolute value of this? 3 minus 2i. So just, sorry. Let's answer this. Turn it to a pen. So 3 squared plus 2 squared. Sorry, a little bit under the weather, so I wasn't able to do the whiteboard thing like I did yesterday. So I was just reusing this slide that I had used uh, during the previous hackathon or lecture series we had. But I added some new materials. 2 squared, take the square root, okay? And so this is going to be 9 plus 4 square root of 13, okay? This is easy, 0 squared plus 1 squared, square root. So this is 1. About this one, 36 plus 9, 36 plus 9, that's 45. So this is square root of 45 or 3 square root of 5. 36 plus 9, tama. 45. Can I see a confirmation from the group if my answer is correct? Were you able to follow the computation of the absolute value? Because this is very important when we go to quantum computing. These numbers, these are your coefficients, the coefficients of your basis vectors, get 0 and get 1. So in order, that's or the probability amplitude. So in order for you to get the actual probabilities, you have to get the absolute value. And sometimes those coefficients are complex numbers. So it's really important for you to know how to compute the absolute values of complex numbers. How about this one? 4 minus 3i. It's easy. It's 5. You have 4 and 3. Okay? 4 and 3. 4 squared, 16 plus 9 squared, and then take the square root. Okay, another important property of a complex number aside from absolute value is its argument. So the argument theta, it's the angle. It tells it tells about the direction of the arrow. So in the argument, or basically the angle here, it makes from on the horizontal real axis, a positive real axis, your theta is called the argument of the complex number. And how is it computed? So that's your modulus, or that's your absolute value. And so this is another form. You can actually represent a complex number with this form. I'm going to deal with this later. This is called the polar form of the complex number. But the argument of a complex number is just the uh, arctangent of the ratio between the imaginary part and the real part. Okay, so that's the argument. And this is another form of uh, complex number. We call this the exponential form. So these are very important representations of complex number. We have the Cartesian form or the rectangular form, and then this is the polar form of complex number, and this is the exponential form of complex number. They are equivalent, or they equal to each other, but different representations and different advantages. This is more succinct. This is more concise. You just have the R, but it doesn't show you the A and the B. But this one shows you the R, and it's also the angle. We would be, from time to time, it would be beneficial to use one form over the other. Okay, let's try multiplication of complex numbers. Since a complex number in rectangular form or in Cartesian form is kind of like a binomial if it's considered as a polynomial. It's kind of like a binomial. As you can see here, if we multiply two binomials, we use the FOIL method. So we're just going to apply that FOIL method with complex numbers as well. Okay, example here. So using the FOIL method, yeah, that's 8 minus 4i. Wait, 8 minus 16i plus 21i minus 24i. Sorry, this is, I think there's something wrong here. That's 12, 16, yeah, negative 16 and 12. So na negative 4i. And then 3i times 3 times 8 is 24. So 24i squared. But since I squared is negative 1, so the final answer is 32 minus 4i, which is also a complex number, as you can see here. In form niya, it's also, the form is also the same. You have the real part and the imaginary part. So that's how multiplication works. So z sub 1 times z sub 2 generally is just like multiplying two binomials. But the nuance here is that you have an I squared that can be restated as negative 1. So using the FOIL method, that's just how multiplication of complex numbers work. And then substitute I squared with negative 1 at the end. Okay, exercise. So I hope you can do this using the FOIL method. You do this first. So you have 10. And then for me, I do this first and then this one. And then the extremes. So 10 minus 15i. And then plus 2i. And then minus 3i squared. 3i squared. So this one is 10. Negative 15 plus 2 is negative 13. I minus plus 3. Okay. So 13 minus 13i. That's the final answer. Let's see. Okay. Got it right. What else? Okay. So this is the advantage of converting one complex number from one form to another. For example, in the exponential form, you can easily see, or even in the polar form, you can easily see the angle. In this case, 2 square root of 2. So this is 2 is your A and 2 is your B. To get the value of R, it's just 2 squared plus 2 squared, and then get the square root of that. That's square root of 8, or that is 2 square root of 2. And E raised to the I pi over 4. Pi over 4 is the argument. There's actually if you're going to multiply a complex number, geometrically, the interpretation is just like a rotation. Like we are just adding the angles. For example, if you convert a complex number into its exponential form and you multiply them, it's basically you can see that angles are just being added together, or meaning the length is not changed, but the arrows are being rotated. Like for example, in this case, this is a complex number and this is another complex number. If you multiply them together, basically since they are exponentials, you just add the value of the exponents. Okay, so pi I over 5 and pi I over 3 is equals to 8 pi over 15. And 8 pi over 15 is this one. As you can see, it's actually being added. Or for example, if you have this angle and you have another angle, you add the two angles. Basically, you're rotating your arrow, okay, based on the value of the angle of the two products, the two factors that you're taking the product of. Now, let's go to division. So for division, okay, we're going to divide two complex numbers. Any idea? Or you already know this, since a lot of you are engineers, probably have an idea of how to divide complex number, we will use the concept of conjugates here again. So in this case, if you have two complex numbers, for example, C plus DI and A divided by A plus BI, excuse me, we multiply it by 1, okay? And that one is expressed as the ratio of the complex conjugates of the denominator, okay? So you get the complex conjugate of the denominator, A plus BI. So this whole thing multiplied by 1 as expressed as the ratio, the complex conjugate based on the complex conjugate of the denominator, A minus BI divided by A minus BI. So that your denominator, because the thing is, okay, the important fact to note is that when you multiply a complex number with its conjugate, the product is always a real number, okay? When you multiply a complex number with its conjugate, the product is always a real number, as we will see here. Okay, so this one, we already know how to multiply complex numbers using the FOIL method, but we also do that here. But this one is easier since this is just a complex conjugate. This then just multiply this like difference of two squares. As you can see, what's the final answer? Let me see. So there it is. A squared plus B squared, which is always a real number. Example. So this is the denominator. What's the complex conjugate of 4 minus I? 4 plus I. So multiply this by 4 plus I divided by 4 plus I. And then simplify. You're going to have this one. Which is 3 over 17 plus 22 over 17I. Okay. So that we can see the A part and the B part. Okay. Powers of I, or the complex, the imaginary, I raised to 0 is 1, I raised to 1 is 1, I squared is negative 1. So if you multiply I with I squared, so I times negative 1, okay, that's negative I. And as you can see, it will just rotate.
777, 25.
Yeah, it will just be in cycles of 4. So what if I ask you, anyone, chat your answer. What is the value of I raised to the 100? Can you chat your answer? I raised to the 100. What's the value? Based on the pattern. You can chat your answer. I raised to the 100. So you have to check if it's divisible by 4. So this is just modulo 4. If it's divisible by 4, it should be 1. Okay, the answer is 1. Negative naman, same thing. So it's just modulo 4. We'll just cycle. I raised to the negative 1 is negative I. So that's going to be 1 over I. Okay, let's compute this one. I raised to the negative 1 equals, sorry, 1 over I, right? 1 over I. So multiply this by its complex conjugate, which is, what's the complex conjugate of I? Negative I. Negative I, meaning negative I divided by I times negative I is negative I squared, but I squared is negative 1. Negative of negative 1 is 1. So that's why we have this I here. Okay. So it's just actually a cycle from the negative numbers to the positive numbers. Oh, now let's go to polar coordinates. In your algebra or in analytic geometry, I think this was discussed. So we have a different coordinate system to represent a point in space or a point in a plane. The conventional thing that we do is we reference, for example, an origin, and then we create two axes, orthogonal axis, so that we could locate the plane based on its distance from one axis, and then the second component would be the distance to the other axis. So that's your Cartesian coordinate system. But you can also you can also locate a point using two parameters: its distance from the origin and the angle it makes on the horizontal axis. So this is the polar coordinates. It's represented by r, or the radius, the distance from the origin, and the theta, or the angle it makes on the horizontal x-axis. So there are some advantages of using polar coordinates over the rectangular coordinates. But if we want to change one from the other, the formula is just easy. R squared is equals to x squared plus y squared to get to the to compute its radius in the polar coordinates, and the angle is just the tangent theta is equals to y over x, or basically theta is the arctan of y over x. So, for example, this is your point in rectangular coordinate 3, 4. You can compute for the r as r squared is equals to x squared plus y squared. So that's going to be 5. And then the tangent theta is arctan 4 over 3. That is approximately equal to what? 0.9273 radians. So now, since we can actually use analogously, we can use the polar coordinate to change the rectangular form of a complex number to its polar form. So the polar form of a complex number is actually this one. This is the polar form of the complex number z. But to compute how to get the r and the theta, you can use this formula. R is just equal to the absolute value of your complex number, or the modulus of your complex number, which is just the square root of a squared plus b squared. And the argument is your theta. Basically, the real part, cosine theta is just the real part divided by the absolute value in this. And or sine, you can also get it from sine theta, just uh, divide the imaginary part with the absolute value. So these are the relationships between the parameters we use to represent a complex number in rectangular form and in polar form. Let's try to multiply complex numbers in polar form. So in polar form, you have that, for example, a complex number r sub 1 cosine theta sub 1 plus I sine theta, and another complex number r sub 2 cosine theta sub 2 I sine theta sub 2. So the product of this number, you can actually get multiply this using, you can distribute this. Let's distribute this and then distribute r here. So you're going to have a binomial. Multiply two binomials. So if you have two binomials, intermediately, you will have four terms. But once you arrange those terms and you apply some trigonometric identities, you will see that you will come up with this formula. The product of z sub 1 times z sub 2 is just the product of the arguments r1 and r2. The modulus r1 and r2, and cosine theta plus the sum of the arguments. Cosine of the sum of the arguments plus I sine sum of the arguments. So if you Just an exercise, you can probably try what I have suggested. You distribute this, and then multiply them together, and then do some rearranging. You will find and apply the sum of the angle, cosine of sum of angles and sine of sum of angles, trigonometric identities. You will come up with this one. So basically, in multiplication, you just multiply the modulus and then add the arguments. Dividing two complex numbers is similarly easy. It is defined as this one. In this case, you divide the modulus and then you get the difference of the two arguments. Example. So we have these two complex numbers in their rectangular form. Okay, we convert them to their polar form. Okay, this is the conversion to the polar form. You get the r is this one, since 2 squared plus 2 squared, square root of that is square root of 8. So that's 2 square root of 2. And the angle is pi over 4. Since 2 over 2, this is 1. Arctan of 1 is pi over 4. Okay? So that's how easy for this one, because it's a special angle. But that's how you compute, or you calculate, or you convert a complex number from the rectangular form to the polar form. So same thing here. And then if we are going to multiply them, basically you just multiply the r's and then add the angles. So when you multiply 2 by 2 square root of 2, that's 4 square root of 2. And then for the angle, it's cos pi over 4 minus pi over 6. And then, sorry, you need to add, okay? But this is negative, so that's why it becomes a minus here. Pi over 4 minus pi over 6. So that's pi over 12. So this is the final answer. And this is in polar form. You can actually change that to rectangular form using the formula that I've presented in a couple slides before. The Moivre's theorem. Okay. Usually you use this theorem if you're exponentiating or if you're getting the powers of complex number. For example, z represented in polar form, z squared will just be squaring the r, and then it's actually you can do that using the multiplication of using the polar form, multiplying by itself. Okay, for example, if you multiply this by itself, you will see that you can generalize that basically you're just getting the powers of r and then compounding the number of angles. For example, in this case, if the power is 2, so the power of your r is also 2, but in terms of angle, you just multiply it 2 times. Same here, z squared is equal to r squared cosine 3 theta I sine 3 theta. So generally, for given z to the n, the formula is r cosine theta plus I sine theta raised to the n, or that is r to the n cosine n theta plus I sine theta. Okay, I think this is the most important equation here for complex numbers. Sorry. It relates the polar form with the exponential form. This is called the Euler's formula, by the way, and it is touted as the most beautiful equation in mathematics. This one is the most beautiful equation in mathematics, in all of mathematics, because you have there the two special transcendental or irrational numbers e and pi. They come up everywhere in natural, in science and in engineering. The number e and pi, they are considered as irrational or transcendental numbers. And you also have the special number I. And then you have the special number 1, which is neither prime nor composite, special in many ways, sana all special. And then 0. is also a special number, just like what I mentioned before. So all the special numbers are there in one equation, and all the important operations, mathematical operations, are there also in one equation. You have addition, you have multiplication, you have exponentiation. That's why it's touted as the most beautiful equation in all of mathematics. And this is derived from this one. Okay, this one is derived from this one. When we let theta equals pi, okay, when we let theta equals pi, this will become e to the I pi. Cosine pi is, okay, pi is somewhere here, so that's -1. Sorry, cosine pi. What is cosine pi? -1. Yeah, cosine pi is -1. What is sine pi? 0. So that's why this one is -1. But you add 1 here, so that's why -1 plus 1 is 0. If we let theta equal to pi, this whole thing will become -1. And then add 1, so that's why you have here 0. Okay, what else? Oh, how did we derive this? How? Okay, there's a lot of, you can find a lot of proof of the Euler's formula, but one of the popular proof is their Taylor series expansion. If you use the Taylor series expansion of I and cosine and sine, you will, and then do a little bit of algebra, since the Taylor series expansion of this is just the summation of something like n factorial. But anyway, these two complements each other. This one is an even function. This one is an odd function. Sine theta is an odd function. So you can Google it on how this equation was derived. But one of the more popular derivations of this most beautiful equation in mathematics is the Taylor series expansion. But there are a lot of proofs. Anyway, having said that, so I've already discussed with the polar form. This is one of another representation is called the exponential form. So if you have this z equals a plus bi. Okay, this is the rectangular form, this is the polar form, and this is the exponential form. We got the exponential form based on this formula. And this is more succinct because you can just easily, it's easier to write. This is more concise. Z is equals to r I raised to the theta, in which r here is the absolute value of your z, and theta is the argument of z, or the angle. Exercise. Now conjugation. Okay, the conjugate of z in their polar form is just r cosine theta minus I sine theta. So if this is z, the conjugate in polar form is this one. The conjugate in exponential form is this one. You just negate the exponents. Okay, so as you can see here, remember that cosine theta is equals to cosine negative theta, since cosine theta is an even function. Okay, when you have an even function, the argument, even if you negate that, it's also the same. For example, generally f of x is equals to f of negative x. Yeah, that's the definition of an even function. Sine is not an even function. Sine is actually an odd function, since an odd function is f of negative x is equals to negative f of x. Okay, multiplication using the polar form. So when we multiply, I think I've already discussed this, but if we're going to multiply using the exponential form, so multiplication will just be this one. Multiply and then add the arguments. Multiply the modulus or the absolute value, and you add the arguments. So if you multiply two complex numbers, what time is it? Oh, time check. It's okay. Let's go back to quantum computing. Now that I have already discussed to you complex numbers, let me go back to quantum computing. So yesterday, I discussed to you the difference between classical computing and quantum computing. In classical computing, we use states as bits or zero, and then we use logic operators or logic gates. In quantum computing, we use states as vectors. You have the ket1 and the ket0, and gates as matrices. So and then the concept of superposition was discussed. When a qubit is in a state other than ket0 or ket1, we say it is in superposition of 0 and 1, meaning they are both 0 and 1 at the same time. For in mathematics, we call that the superposition. We call superposition as linear combination. So yesterday, this is the representation. I show you the representation of quantum state, ket psi, and it's actually a linear combination of ket 0 and ket 1, where and the important thing here is that the absolute value, the square of the absolute value of alpha and the square of the absolute value of beta, the sum of them should be equal to 1. And we call these as probability amplitudes or amplitudes. Now, we need to square them and get the absolute value to come up with probabilities. But I didn't mention yesterday that this alpha and beta should be complex number. Okay, that's why I introduced to you the concept of complex number. And aside from that, I'm going to introduce other two important states. The state plus, it's also a vector. State minus, uh, and then ket plus, ket minus, ket I, and ket negative I. And these are their representations. 1 over square root of 2, meaning equal superposition of being 1 and 0. This one equal superposition of being ket 0. And see the difference here? This will play out a lot. This is especially when we talk about the phase. Sorry. Yeah, in phase. Sorry. And then ket I is, already have here the imaginary number, a complex number. Okay, and then ket negative I. So these are their representations. Now we include i's. So we have we added additional important quantum states. Ket, aside from ket 0, ket 1, ket plus, we now have ket plus, ket minus, ket I, and ket negative I. Example of qubit states. So these are some example of qubit states. Now I'm including complex numbers. Yesterday, I only gave examples of states that are not complex number, but basically a alpha and beta is an element of complex number. This is also an example. As you can see, this is an example of a complex number in exponential form. So in books or in literature, you're going to see these coefficients as either in exponential, in polar, or in rectangular form. So be very familiar with these notations. So this is an example of a qubit state also, and this is also an example of a qubit state. As you can see, they are all now complex numbers. Oh, wait, how can we verify that these are, it says there, can you verify this? Okay, we can verify that. Okay, how? Using this formula. You get the square root of the absolute value of these and get the square and see if they add up to 1. Okay, so let's try this one, 2/3. 2/3, get the absolute value squared plus, what's the absolute value of this one? Anyone? What's the absolute value of this one? Absolute value of 1 minus 2i. over 3 squared, you will find out that, okay, let me check. Can you compute for the absolute value of 1 minus 2i over 3? Anyone in the chat? If you really know how to compute for the absolute value or the modulus of a complex number. This one is easy. 2/3 is just 2/3. Okay, so squared, that's 4 over 9. One minus 2i, that's 1 squared plus 2i. Okay. 1 squared plus 4, that's 5. 3 squared, 9. So 5 over 9. Okay, I hope you're able to follow to why I was able to come up with 5 over 9. 1 squared and then 2 squared. So 1 squared plus 2 squared, you have 5 squared, and then 3 squared is 9. So 4 over 9 plus 5 over 9 equals 1. So this is checked. So basically, that's how you check if these are valid qubit states.
We can represent a qubit graphically on what is called a block sphere. On the top, we have the 0 state, and on the bottom, we have the 1 state. On the horizontal, we have the plus state, minus state, I state, and negative state. We will discuss these in later lessons. The closer up the qubit is to the 0 state, the higher probability of measuring the 0, and the same goes for the 1 state. That means that if we have the state 1 on root 2, 1 on root 2, it will lie halfway between the north and south poles, has an even chance of being measured at 0 or 1. You may notice that since it is a sphere, qubit can spin around the sphere.
Elmer, excuse me.
Yes.
We will talk about this in later lessons.
Baka hindi mo yata na-share yung sound.
Now, it is
Para siyang galing sa laptop lang.
higher up the qubit,
Would you like to connect
likely
again and share with sound?
likely we are to measure a 1. Pause the video and think about where the state 1 on 2
Sorry about that. Let me share again.
We can represent a qubit graphically
How about now?
on what is called a
Ganda.
block sphere. On the top, we have the 0 state, and on the bottom, we have the 1 state. On the horizontal, we have the plus state, minus state, I state, and negative I state. We will discuss these in later lessons. The closer up the qubit is to the 0 state, the higher probability of measuring a 0, and the same goes for the 1 state. That means that if we have the state 1 on root 2, 1 on root 2, it will lie halfway between the north and south poles, since it has an even chance of being measured as 0 or 1. You may notice that since it is a sphere, the qubit can spin around the sphere. This is called phase. We will talk about this in later lessons. Right now, it is important to understand the basic idea that the higher up the qubit is, the more likely we are to measure a 0, and the lower the qubit, the more likely we are to measure a 1. Pause the video and think about where the state 1 on 2 root 3 on 2 will be on the block sphere. The qubit 1 on 2 root 3 on 2 would be halfway between the equator and the 1 state, since it has a 1 on 4 chance of being measured as a 0 and a 3 on 4 chance of being measured as a 1.
Okay, now I introduce you to the black sphere. Yesterday, when I was discussing the different quantum states, I use a unit circle. But now, since we already involve complex numbers. Complex numbers are very important because in quantum mechanics, where what we're trying to model the physical properties of quantum mechanics, complex numbers comes up a lot. Like for example, in the Schrodinger's equation, there's a complex number. There's an I there in the Schrodinger's equation, and usually in quantum mechanics we use wave function, which also involves a lot of complex number. That's why we need to understand complex numbers, and that's why complex numbers come. We need to use complex numbers to represent quantum states. Okay, and another thing, the properties that was introduced to you yesterday, like for example, superposition, interference, entanglement, all of them, you will need complex numbers with all of them. Now, in order to represent a simplified representation of a to give you a simplified representation of a quantum state, we're going to use this black sphere. Okay, yesterday I showed you a unit circle, but that won't really able to generalize to represent some complex number. But if we want to represent complex number, we're going to use a black sphere. So in a black sphere, basically it's just a spherical coordinate. Okay, a spherical coordinate, a unit sphere, if you have spherical coordinate wherein your r, because in a spherical coordinate you use three parameters to determine a point in space. You have the r, which is the length of your vector, or the distance of the point from the origin, and then you need two angles. Okay, the angle it makes on one of the axis and the angle it makes on the other plane, or orthogonal to the other axis. Like in this case, theta here is the angle you make with the z-axis, and phi here is the angle you make with the angle within in the on the xy plane that it makes from the x-axis. So theta measures the angle down from the North Pole, called the polar angle. So theta from the North Pole to the, it's called the polar angle, and phi measures the angle across the x-axis in the xy plane, called the azimuthal angle. So the range of theta is from 0 to pi, while the range of phi is from 0 to 2 pi. So basically, you don't need the range of theta to be 2 pi, because it's going to be redundant or superfluous already, because you, based on that range, you can already determine any point on the black sphere. We don't need r here is equals to 1, since this is a unit sphere, and any point on the black sphere is a valid quantum state. Okay, so we're going to represent n quantum state as a point on the black sphere. So get familiar with the black sphere. It's just a spherical coordinate system where where you can use the theta and the phi as parameters. So I'll start with this one. This ket psi is a general representation of your quantum state, and I mentioned yesterday that it is equal to, it is a superposition of the ket 0 and ket 1, where alpha is the probability amplitude of getting a 0, and beta is the probability amplitude of getting a 1. Okay, and alpha and beta is an element, is a complex number. But if to represent this ket psi on a black sphere, or any quantum state on a black sphere, we're going to make some conventions, okay? Some simplifications. So using, we would like to make the coefficient of ket to be just real, and then the coefficient of 1 to be a complex number. And then we will just use theta and phi, so that we can actually simplify the number of parameters. So any point represented, any point here in the black sphere, we can actually locate using by just specifying theta and phi. So as you can see here, this one, A is alpha or B is beta. Since they are complex number, we represent them, we convert them to, this is the conversion, the derivation of the, or the simplification of the representation of a quantum state on a black sphere. So we have here alpha, which is a complex number, and B is also a complex number, so we can represent them in their exponential form. R sub 1 E phi I times I, and then R sub 2 E raised to the phi 2 sub I get 1. And then since we can actually factor in E to the phi I, here it's being factored, and then so that you'll have just R1 here with on ket 0. But since you have already, you factor this, you're going to have your phi 2 minus phi 1, which is the, which is called the relative phase. Okay, this one is called the global phase, which in quantum mechanics we can actually discard, and meaning it's physically the same, even if we don't, the quantum state is physically the same even if we don't have this one. This is the global phase. So that's one of the simplifications here. We can remove the global phase, and what is important and will play out a very important role is the relative phase, which is going to play a important role when we talk about interference. So basically with e to the phi I in C with absolute value equal to 1, so we can just remove this. So the representation now becomes A sub 0 plus B sub 1. It will now just be this one, R sub 1 of 0 plus R sub 2 E raised to the relative phase here, or P sub 2 minus P sub 1 of I times ket 1. The coefficient of A is real for simplicity, and this one is complex. So the new representation, if we're going to use a black sphere, the conventional way of representing a quantum state is now this one. We have here the coefficient of the ket 0 as a real number, and the coefficient of ket 1 as the a complex number. So now we're just left with 2 degrees of freedom. So we just have the R and the phase. One related to the magnitudes and the other one related to the relative phase. And relative phase is more important than the global phase. So the state of a single cubic psi can be represented by this one, R sub 1 ket 0 plus R sub 2 e to the phi I ket 1. So you can see here R sub 1 is a real number, R sub 2 is a complex number. And we have to make sure that R sub 1 squared plus R sub 2 squared is equals to 1. And phi is the phase, the relative phase between an angle between 0 and 2 pi. So since R1 is equals to cosine theta over 2 and R2 is equals to sine theta over 2. So this is the representation with the theta. So if you have a point in the black sphere, for example, your theta here, okay, this is your theta and this is your psi. Okay? And if you want to convert to go back to the XYZ representation, if you don't from, for example, from spherical to the rectangular coordinate, this is the formula. X is equals to sine theta cos phi, and y is equals to sine theta sine phi, and z is equals to cosine theta. I'll be discussing a more in-depth explanation of this next year. But in the meantime, I want you uh, to accept the fact that I want you to use this representation of a quantum state on if we're going to represent it visually on a black sphere.
On the Bloch sphere, we saw in the previous lessons that we could also rotate around the z-axis. This is called phase. It may not seem very useful, as the probability of measuring a 0 or a 1 is still the same, no matter how much we rotate around. But phase is what makes quantum computers as powerful as they are. We will get into the uses of phase in the next lesson.
Wait, before I continue the video, I'd like to explain that in the black sphere, we designate the north of, for example, think of it as a globe. Okay, the black sphere as a globe. So you have the North Pole and the South Pole and the equator. Okay, the North Pole is we designated with ket 0, and the South Pole with ket 1. So ket 0, this one is 1, 0, and this one is 0, 1, right? And we now have complex numbers here. So this one, if that is the case, so you have here the equator. Okay, the equator, any point here is equidistant to ket 0 and ket 1. Okay, so any point here is equidistant to ket 0 and ket 1. And you have here a special quantum state like the ket plus and the ket minus, and this the ket plus is totally opposite the ket minus, and ket I is totally opposite, or diametrically opposite ket negative I.
In this lesson, we will see how we can represent phase mathematically. To represent phase, we have to bring back our old friend, complex numbers. In quantum computing, we mostly use complex numbers in exponential form. You will now see why. But first, let's consider some states in the Bloch sphere. Let's first consider the states 1 over root 2, 0, plus 1 over root 2, 1. If we apply a z gate, we get it to the state 1 over root 2, 0 minus 1 over root 2, 1. As you can see, the 1 state was multiplied by a factor of negative 1, and the qubit rotated pi radians around the z-axis. If we represent the negative 1 as a complex number in exponential form, we get e to the I pi. Notice how the angle of the complex number is pi radians. Let's try another example. Let's plot the state 1 on root 2, 0 plus 1 on root 2, 1 and 1 on root 2, 0 plus I on root 2, 1. If we represent I as a complex number in exponential form, we get e to the I pi over 2. And if you look at the Bloch sphere, to get that state, we rotate pi over 2 radians around the z-axis. We use complex numbers in exponential form in quantum computing since it gives us a nice mathematical way of rotating around a circle by changing the value of phi. By multiplying the 1 state of the qubit with the complex number e to the I phi, we rotate the qubit around the z-axis by phi radians. But why is it the 1 state and not the 0 state being multiplied by the complex number? There are two types of phase, global phase and relative phase. Global phase is when the entire qubit is multiplied by a complex number, and relative phase is when just the 1 state is multiplied by a complex number. It turns out that global phase is physically irrelevant. So the state e to the I phi times 1 over root 2, 0 plus 1 over root 2, 1 is logically equivalent to the state 1 over root 2, 0 plus 1 over root 2, 1. Relative phase, on the other hand, is extremely important and matters in our calculations. Relative phase is when the amplitude of the 1 state has a factor of a complex number. As we saw earlier, having relative phase rotates the qubit on the Bloch sphere around the z-axis. But what if we have a complex number in both the amplitudes of the 0 state and the 1 state? What we do is we factor out the complex number of the 0 state from the entire qubit, creating a global phase and relative phase. Then we can discard the global phase, leaving us with a qubit with a relative phase. We saw previously on the Bloch sphere that phase does not affect the probability of measuring a 0 or a 1, as the qubit stays the same distance from the 0 state.
Just would like to highlight the fact that the z-axis is this one, and then the x-axis is the axis wherein the plus minus reside, and then the y-axis is where the ket negative I and I reside.
State and the 1 state, no matter how far we rotate around the Bloch sphere. If we look at an arbitrary qubit state, alpha 0 plus e to the I phi beta 1, the probability of measuring a 1 is the magnitude of e to the I phi beta squared. We can split the absolute values up like this. The magnitude of e to the I phi is 1, since the coefficient of the complex number, in exponential form, states its magnitude. So the probability of measuring 1 is still the magnitude of beta squared. In the next lesson, we will see why relative phase matters.
Okay, so that's the black sphere, and these are the different states that I have just enumerated a while back. So we're already familiar with ket 0, and it's a column vector 1, 0. And on the black sphere, the value of theta, as you can see, the theta is the angle it makes latitudinally navigating the latitudes of the sphere, okay, from the north pole to the south pole. So that's the theta. So that's 0, meaning it's here. Okay, just use a laser pointer. It's here. Okay. Oh, sorry. And then phi is 0, because the angle phi is actually the angle, the 2 pi here. The angle is measured from the x-axis. And then ket 1 is 0, 1. And the angle theta is from here, because this is the reference angle, from here to here. So that's pi. That the angle theta that you make, or the polar angle, is pi. But the azimuthal angle is 0 also. And then ket plus is here. It's actually on the equator. Ket pi, plus, ket minus, ket I, and ket negative I are on the equator. There's a plane on the equator, and they are, ket plus is orthogonal, is diametrically opposite ket minus, and ket I is diametrically opposite negative I. So these are the column vector 1 over square root of 2 of 1, 1. And the angle it makes, the theta, is pi over 2. And since this is plus, so the angle starts here. The azimuthal angle starts here. But for minus, you move from here to there. So that's pi over 2. Oh, sorry. Ket minus is, sorry, pi over 2. But the azimuthal angle is pi. Okay, from here to here. Okay, and then ket I is here at this point, and its column vector representation is 1 over square root of 2, 1 I. And then, so basically think of this plane as the complex plane. This is the real axis, and this is your imaginary axis. Okay, this is your positive imaginary, this is your negative imaginary. Okay, this plane here that cuts across the equator is your complex plane that I discussed in the previous slide. So as you can see, the angle of ket pi is pi over 2. Since from here to here is pi over 2, and I is pi, the value of the azimuthal angle, or phi, is pi over 2, because from plus to here is pi over 2. Okay, and then for negative I, 1 over square root of 2, 1, negative I. So that's this point. The angle from here to here is also pi over 2. And the value from here to here is 3 pi over 2. From this one to that one is 3 pi over 2. So those are the 6 states on the black sphere. Now, locating a qubit on the black sphere. As you can see, the theta, the theta here represents how far is a given state. Is it nearer to the north pole, which is ket 0, or to the south pole, which is ket 1? Okay. But if it's in the equator, it's actually in equal superposition. But there's a lot of points here. There's a lot of points that are in equal superposition between ket 0 and ket 1. So locating a qubit on the black sphere. How do we do this? Can you locate the following on the black sphere? So, for example, given this one, that's 2/3, and we have already computed this. This is 49 over 5 over 9. So 5 over 9 is greater than 49, meaning that this point should be nearer the South Pole. Okay? This point should be nearer the South Pole. About the other one, okay, I'll just leave them as exercises. But basically, you can compute for the angle, theta, given the formula that I've shown you in the previous slide. And then you can somehow locate these points in the black sphere or estimate where those points are. Now let's go to the sample computation that I discussed yesterday. I mentioned that from a single state, we can manipulate those states by subjecting them to quantum gates. So that's basically how some computation works. We subject each quantum state to a series of quantum gates, and then later on, or along that line, we can do some measurement or observation. So how do we operate with qubits? The same way we operate with bits using matrices. Like in this case, this is an example of a matrix, and this is an example of a quantum state. So basically, we just multiply it, and then the resulting product is another quantum state. So what are quantum gates? Quantum gates act on qubits like logic gates act on bits. So I have already discussed this, but yesterday we didn't choose complex number. But now, since I have already introduced you the black sphere, and any point on that black sphere is a valid quantum state, then you can now use some of the you can now subject them to quantum gates. Okay, we need to make sure that the total probability must remain 1. So that's why I introduced you to the concept of unitary matrices. Later on, next year, I'll be discussing unitary matrices, what are Hermitian matrices, what is an adjoint of a matrix. So more on those for next year. But for now, I just want to show you the implementation of the quantum computation using the mathematics of or the linear algebra and some complex numbers. So yesterday I just put there a square that says quantum gates, but now we can now identify what these quantum gates are. The first one is the identity gate. So the identity gate turns 0 into 0 and 1 into 1, hence doing nothing. This is the identity gate, identity matrix lang to. Okay? For example, arcade 0, multiply that by I, wala siyang gagawin. It's just, it will remain the same. I times, so it's not doing anything. But it's important. Okay, the Pauli X gate or the NOT gate, okay, it's synonymous with the NOT operator in our classical computing. Pauli X gate, so it's represented by capital letter X. This matrix, this is the Pauli X gate. It's kind of like the I in reverse, but 0 on the main diagonal and 1 on the other entries. Okay, X times 0 is 1, X times 1 is 0. So that's the effect of this. If you multiply this with the ket 0 and ket 1, it will just reverse. Basically, in the black sphere, what happens is, if you're 0 and you transform it using the Pauli X gate, it's just going to do a rotation. Okay? Rotation of your axis. And if you do it another one, if you multiply it with the X again, it will go back to its original point. Okay, if it will go back to its original point. So basically, X squared is equal to I. You can try that. You can multiply X times X, and you will see that it's equal to I. X raised to the 1000 is equals to X. X raised to an odd number is equals to x. X raised to an even number is equals to the identity matrix. So that's the effect of applying the X gate, the poly X gate. It's going to rotate along the X axis by pi. Yeah. If it's going to rotate along the X axis by pi, so if you have your original point here and it's going to be rotate, if you apply the X gate, it's going to end up here. Okay. Next, we have the Pauli Y gate. The Pauli Y gate turns 0 into I times 1 and 1 into negative I times 0. So these are examples. So this is the Pauli Y gate. So you multiply this with your and that is the effect. But in the black sphere, if you have a point here, it's just like a rotation along the y-axis. Okay, the Pauli Z gate keeps 0 as 0, but turns 1 into negative 1. Okay, turns 1 into negative 1. It doesn't affect 0, but it turns 1 to negative 1. So this is the matrix representation of your Z gate. And on the black sphere, it's basically you're doing a rotation along the Z axis. Okay, for your exercises, calculate Z raised to the 217, X raised to the 101, Y raised to the 50 of alpha ket 0 plus beta ket 1. What is the value of y squared? Okay, and the value of z squared. So try multiplying it to itself and see what will happen. Since it's just a rotation, so basically when you multiply this with itself, it should end up to the same place. So y squared is also the identity, and z squared is also the identity.
With classical computers, we use logic gates to process data. With quantum computers, we still use gates to change the states of our qubits. Y, and apply the X gate to it, it flips to the 1 state. Let's try a qubit that is halfway between 0 and 1. Try and see if you can figure out what the X gate is doing. Let's try a qubit in this state. As you can see, the X gate flips the qubit 180 degrees or pi radians around the x-axis. Now let's have a look at the Y gate. Here are some examples of the Y gate transformation. As you can see, it does the same thing as the X gate, but instead it rotates the qubit state 180 degrees or pi radians around the y-axis. Lastly, we have the Z gate, which rotates the qubit 180 degrees or pi radians around the z-axis. Since these gates rotate the qubit around the specified axis by pi radians, if we apply the same gate twice, one after the other, then the qubit returns to its original position. This means that these three gates are their own inverses. We can represent these gates as matrices. Here are the matrices for these gates. For the moment, ignore the complex numbers in the Y gate matrix. We will explain this later in the next lesson when we talk about phase.
Okay, important one qubit gates, the phase gate. Aside from your poly gates, you also have the phase gate. The phase gate S is the square root of the Z gate. So S ket 0 is equals to 0, S ket 1 is equals to I 1. So this is the matrix representation of your S gate. And it just rotates instead of pi, it rotates it pi over 2 or 90 degrees. The P gate is also a rotation phase gate. The P gate, also called the pi over 8 gate, is the square root of S. Okay? So this is the matrix representation of your P gate. It rotates along the z-axis, but just by pi over 4.
Now that we understand relative phase, let's introduce two new gates, the S and T gates. The S gate adds a relative phase of pi on 2 radians. The T gate adds a relative phase of pi on 4 radians. If we take the conjugate transpose of the two matrices of the two gates, we get their inverses. For the S gate, we can see that applying S dagger adds a relative phase of negative pi on 2, which is the inverse of the S gate. This means that if we apply a S gate, then an S dagger gate, we are back in the same spot, meaning the S dagger gate is the inverse of the S gate. We also have the T dagger gate, which is the same thing as the S dagger, but adds a relative phase of negative pi on 4 radians instead, meaning it is the inverse of the T gate.
And now this is probably the most important gate in all of quantum. I think arguably the most important gate, the Adamar gate. Okay, the Adamar gate turns zero into plus and turns one into minus. So this is the Adamar gate, the matrix representation. It's 1 over square root of 2. Then you all have 1 there except for this one, which is negative 1. So what it does is when you apply h to a 0, it turns into 1. When you apply to 1, it turns into minus. Okay, so this is the Adamar gate. Let me just play this video.
Before we discuss perhaps the most important gate in quantum computing, we will quickly revisit the Bloch sphere. In earlier lessons, we saw that on the equator we have 4 states: the plus state, minus state, I state, and negative I state. Now that we know about phase, we can define these states. All they are a shorthand for commonly used states. Since they all lie on the equator of the Bloch sphere, they all have an even chance.
Sorry. Anyway, I'll just show that video later. But basically, what it does is the Adamar gate is it rotates it to along this axis, the x plus z axis. The Adamar gate takes 0 or 1 bit and puts it exactly into equal superposition. So that's the important part here. For example, if you have 0 here, when you apply the Adamar gate, it converts it to the plus, and if you have a 1 here, it converts it to the minus. So this is a summary of the 1-qubit gate identity, the poly gates, X, Y, Z, the phase gates, and the Adamar gate. But there are also other gates like rotation gates, so you can specify the angle of rotation, and the phase shift gates. Okay, sequential quantum gates. So we use linear algebra when we compute the effect of gates. So basically, you can apply a series of gates, H, S, T, H, but when you multiply them, it's from the right to the left. So you multiply this first, and then you come up here. And then you do this first, and then once you already have that, you now include this one in your computation up until you reach this point. So this is sample computation. Okay, that's the final answer if you are going to compute the effect of a sequence of gates. And there, I think this is a very important concept also, quantum circuits. Since you already have a knowledge of gates and quantum states, now you can now create your circuit.
This representation of qubits is great, but what if we wanted to apply a gate to a certain qubit? How would we indicate that we wanted to, let's say, apply an X gate to the second qubit in this state? For this, we use a diagram called a quantum circuit. Here is an example of one. On the vertical, we have the qubits, each line representing a singular qubit. The states on the left are the initial states of the qubits. The boxes are the quantum gates, and the letters on the boxes are the type of gate we are applying. For example, this is an X gate. These boxes are measurements and represent us measuring the qubit. The horizontal is the order in which we apply the gates. We start from the left.
Yung measurement, ito yung observed na sinabi ko yesterday, no?
And we have the qubits, each line representing a singular qubit. The states on the left are the initial states of the qubits. The boxes are the quantum gates, and the letters on the boxes are the type of gate we are applying. For example, this is an X gate. These boxes are measurements and represent us measuring the qubit. The horizontal is the order in which we apply the gates. We start from the left and go to the right. Sometimes you will also see psi states pointing to different points in the circuit. These are used to represent the state of the system at different points during the algorithm. Let's go through this circuit. At psi sub 0, we have the state 001. Then at psi sub 1, we apply an X gate to the second qubit. At psi sub 2, we apply a Hadamard gate to the second qubit, giving us this state. Then at psi sub 3, we apply an X gate to both the first qubit and the third qubit, giving us this state. Then at psi sub 4, we measure the qubits, so we will get one of these states with these probabilities.
Okay, now based on that, you saw how do we work with multiple qubits? Because in that video about quantum circuits, it has already shown you that it's working on multiple qubits. So how do we somehow aggregate those single qubit into multiple qubits? So that's actually an operation called tensor product. So we use tensor product of vectors to aggregate uh, uh, to multiple qubits. So to come up with multiple qubits. For example, you have the vector here. This is called the tensor product. You have, and this is the computation of the tensor product. So basically, you have here the first vector, and then you multiply each one with the second vector, and you'll be able to come up with this one. So in illustration, if you want to get the tensor product of 1, 2, and 3, 4, so this is a from single qubit, and now this is a 2-qubit system. So 1, 2, so 1 times 3, 4, so this one, and then 2 times 3, 4, so this one. So that's how you compute. For example, if you want to concatenate 3 single qubit into 3 qubit system, so this is an example. You get the tensor products of these vectors.
If we have multiple qubits, we represent them through the tensor product. For example, if we had 2 qubits in the 0 state, then we would represent the state like this. This is usually shortened to this, where we have the 2 zeros in the 1 ket vector. If we wanted to represent 2 qubits in superposition, we can expand it out like any other operation by multiplying the amplitudes of the states and using the tensor product on the 0 and 1 states. As you can see, now we have 4 states, the 0, 0, 0, 1, 1, 0, and 1, 1 states. This makes sense since those are the possible combinations of zeros and ones we can have with 2 qubits. Measurement works the exact same as before. The probability of measuring 0, 0 is the magnitude squared of the coefficient of the 0, 0 state, and so on. Here is an example of combining these 2 qubits. If we wanted to add another qubit to the system, all we need to do is tensor it onto the end of the state. We also have some shorthand notation you will sometimes see. If we have n zeros, we can write it like this, which means 0 tensor with itself n times. So this state would be shorthand for 5 ones.
Okay, so that's how we represent multiple qubits using tensor product. And I think there are for multiple qubits, there are other types of gates like the Toffoli gates for a 3-qubit gate. And I'm just showing here a comparison of the classical gates and the quantum gates. We have in the classical sense, we have the NOT gate. In the quantum sense, we have the X gate, the AND, the Toffoli gate, the OR, anti-Toffoli XOR. We have also the CNAT, which I'm going to discuss next year, the NAND, also a Toffoli gate, the NOR, and then the anti-Toffoli gate. So these are the different it's how we compare the different gates, logic gates from the classical computing and the quantum computing world. So, okay, key takeaways. I don't want to overwhelm you with a lot of mathematics, so I've just shown you for me what are the important parts based on what I have discussed yesterday. So that's the different gates are basically just matrices, and but later on I'm going to later on in the lecture I'm also will be discussing linear transformations and linear operators, which are probably just the same thing. And then key takeaway here, qubits can be in superposition and are probabilistically collapsed to a classical bit by measurement. And then quantum gates are just linear maps or linear transformation or linear operators or matrix multiplication that keep the total probability equal to 1. Matrices represent operations on qubits. So a qubit state is just a vector. Each quantum gate can be represented by a matrix, and the application of gate to a qubit is a matrix vector multiplication. Operations on bits are represented by matrix multiplication on bit vectors. Quantum computers only use reversible. I removed this, but I'll be discussing that next year. The Adamar gates take 0 and 1 bits to equal superposition. So it takes it from the pole to the equator. And the multi-qubit system are tensor products of single qubit systems. I haven't discussed this yet. And then complex operations can be built by combining sequences of quantum gates in a quantum circuit. I know it's it's a very complicated, there's a lot of complicated math involved, but that's just, I just showed you some of the mathematics, even though if you haven't really grasped it totally, what I really suggest is you watch the videos, and then the materials that we're going to share, you peruse them, and then you try out for yourself so that you can get the hang of it. For example, if you want to try the exercises that so that's going to be very helpful. And with that, if and I give now the screen and the mic to Jabez.
Awesome, awesome. Thank you po again, Sir Elmer, for that very wonderful, um, actually, super overview na siya, no? Imagine, complex numbers pa lang, that's already a semester of classes sa amin sa engineering. And yeah, even combinations, matrices, all of those have mag-iisang semester yan. Pero Sir Elmer was able to um, put it together into liquid gold, and yeah, really put kung ano talaga yung kailangan on quantum computing. But yeah, don't worry guys, we had 2 hours of productive math, and I'm sure na minsan medyo mushy na yung utak natin, no, pero hopefully, no, throughout as we prepare you guys with the math, no, we think that math is inevitable, no, so that we can represent this physical phenomena better, no, pero as we go along, we assure you na you would be able to appreciate all of it, especially when we're talking about gates na and physical representations of qubits. And as we go along and create the circuits, no, yung sunod-sunod na gates, we can see really kung ano yung diniscuss ni Sir Elmer, we can apply those concepts, and then yeah, we can represent those quantum phenomena as those yung sinabi ni Sir Elmer kanina. Okay, so I would also like to call on Sir Bob. Hello po, sir.
Hi, Jabas. We're going to have a break.
Yes, okay po. All right. So, yeah, let's have a 10-minute break, and yeah, you can get some snacks, and yeah. Thank you, Keith. Okay, see you guys in 10 minutes.
Assemble.
Hello guys, welcome back again. Ayan, thank you Keith. Ayan, welcome back again. So we hope that you had a great 10-minute rest and yeah, nakapagpahinga kahit pa paano ang ating mga brains. Okay, moving forward. Next slide please. Let's have an energy check. Ayan, kamusta pa guys? Okay, so type 1 if you relate to that cat. Type 2 if interesting or 3 type 3 if motivated. Ayan. So let's see what ano ba yung energy nyo ngayon right now. Wow, may mga 3 motivated. Wow. Even if it's the end of the week ha. Ayan, great job. Interesting. Ako personally medyo mix na ng 1, 2, 3 eh.
Superposition.
Ayan. Oo, superposition po. Ayan. Ano ba yan? 1/3 tas naka-square root. So, 1 over square root of 3. Ayan. Gets. Ayan. 1 over square root of 3 get 0. Ay, you get 1. Ayan. Anyways, ayan. We still hope that you still have a bit more energy for our next session. And yeah, right before we had some math and now we will still have some a bit more logical as well. And yeah, it's more as we know now, Python has been really popular in almost every field that we know, and because of its ease of use, and quantum computing is not an exception there. So well, we use Python so that the non-programmers, we should say, that the non-programmer professionals like engineers, physicists, would still be able to do what they need to do without the learning curve of learning a completely or syntax heavy language, we should say. So yeah, right now we will have some brief overview, or should I say recaps, because I'm sure most of you, based on your survey that we got from you guys, that you're quite knowledgeable with Python already. But so that we're still on the same page, we would like to get you up to speed. And even if baka, it was quite some time before you had it again. So yeah, at this point I would like to call on, next slide please Keith. Thank you. There we go. So I'd like to call on Sir Bobby for the second session. Again, Sir Bobby is the president of Quantum Philippines and also a member of the Quantum Technology Board of the OST Sure. So yeah, hello po Sir Bob. Good evening.
Yeah, hello guys. Yeah, so this will just be a very light material now because the material earlier was ano yun eh, medyo heavy and it's already Christmas now, so I don't want to burden you anymore, no. Yeah, so so why is it na super light lang yung ano? It's because itong Python programming, well, simula muna siguro tayo sa ano, bakit Python yung gagamitin natin, no? So Python gagamitin natin is because we are going to use the Qiskit framework, no? It's a framework by IBM. Tapos nung sisimula pa kasi ako sa quantum computing, there were a lot of choices, no? I na tiningnan ko ano ba talaga yung magandang gamitin. So yung Microsoft kasi meron siyang ano Q#, no? Problem lang with Q# is that ano its programming language is C#, no? So I mean okay lang sa akin dati because I'm also a Java programmer, so ano siya, madali lang syntax, no? Pero the thing is, during that time, the Q# did not work on the Mac, no? And that was a big disappointment. So kaya sabi ko, sige, ito na lang Python kasi ano to, it's very easy, no? It's very easy. I mean, it's probably the first language for kids, no? Sabihin na natin second language. Pagawin mong first language yung Scratch, no? So Python is easy, and it's also the favorite of mathematicians, no? So very basic lang siya, and we just have to review lang, no? Yung mga basic data types, string, numbers, arrays, list, tuples, and how to define functions, no? So probably most of you know this already, no? Pero it's possible na because we are also in a open session, no? So we also invited other people to attend, no? So mas maganda din if they don't know anything about Python, at least malaman nila ano yung what is this all about. So yeah, so Python is ano siya, it's if you are already a professional programmer, no, it's very easy to learn, no? Sabihin lang natin in 1 hour, you can learn it already. In 1 day, pwede mo nang gamitin yung mga libraries, no? So ganun siya ganun siya kadali. Especially if you're already a programmer, no? Madali na lang yung But probably if you're not a programmer, siguro, but it's a good first language. So dito sa gagawin natin, I'm not going to introduce any features like yung mga advanced features, no, like mga lambda functions, streaming functions, input output. We're not going to read or write any files, no, for regular expressions, no. And at the moment, we are not going to introduce any libraries, no, but we are going to introduce them later, next year na, no. Merong nagtanong sa akin, no, sabi niya, possible ba na can I begin quantum computing just by uh, downloading just by doing Qiskit kagad? So sabi ko sa kanya, mukhang mahirap, no? So pero sa isip-isip ko, parang na-remember ko yung yung isang yung problem now. It's the probability of a monkey, no, that is just typing random keystrokes on a keyboard to produce the greatest play of Shakespeare. No? It's a very small probability. Yung point lang doon is magsisimula ka talaga sa basics, no? So, for example, yung ginawa ni Elmer, that was the basic, no? In fact, sa talaga, sa lecture natin, itong programming na with Qiskit falls at the latter part na, no? Latter part. Kung meron tayong, let us say, 12 na sessions, no? Nandun siya sa mga pang-walo, no? Pang-walo, pang-siyam. But this one is just to make sure that we are on the same page, no? So it's, you know this stuff already. This is just a review. So Python is a language, no, that was created by Guido van Rossum. Last time I heard, nasa Google. So it's high-level language. It's a favorite of mathematicians. No? Kasi itong Python kasi, ang itsura niya parang pseudocode. No? So, and it's a very familiar territory for mathematicians. No? It's also interpreted. Kaya hindi siya kasing bilis ng C. No? Pero it leverages some libraries that are written in C. Kaya pag kinol yung mga libraries na yan, mabilis na rin siya. No? It's dynamically typed, no? Hindi kagaya ng ibang languages like Java, no, or Rust, no, that are statically typed. Alam mo talaga yung type, no, to make sure na nothing gets transformed in the middle of the execution, no. So kaya medyo din to, you have to be careful dito sa sorry. I'm not sharing my screen. Sorry guys, am I not sharing my screen?
Ayan, okay na pa, sir.
Oh, sorry. I did not know. Feel free to speak, no? Feel free to speak, no? Interrupt me anytime. Yeah, open source, no? So it's tagal na tong Python. I remember 1990s, no? Nagamit na to ng kaibigan ko, yung Python. Okay. So let's review, no? So ano ba yung mga if you want to learn a new programming language, ano ba yung mga importante to, no? So simple lang naman, variables, no? And then how to tapos yung mga conditionals, no? If then else, then how to define functions. And then syempre kung gusto mo na medyo advanced, no? how to read and write to a file, no? Tapos kapag abstracto, you can read and write to anything, no? Like for example, FTP, no? Or URL, download a file. So madali na lang siya. So we start with variables. Yeah, so sa Python, naming convention, no? We can use numbers, letters, underscores, pero our variables cannot start with a number. So but we can start with a letter or an underscore. Tapos case sensitive siya, no? So for example dito my var and itong puro small letters na my var, they are different. And also don't use reserved keywords, no? Sa Python. And then when you assign, so when you have defined your variable now, then you can assign something into it, no? So the assignment is simply just putting an equal sign between the variable and the value. Okay. Tapos ito yung mga usual na data types, which is also found in other programming languages. So numbers, integers, and then floating point numbers, and then usual operations, no? Subtraction, addition, and then itong mga exponentiation, no? Ito yung exponentiation modulus, ito yung gagamitin natin, no? When we are doing some, when we are cracking the RSA, no? Gamit na gamit natin yan. Strings, no? So we all know what strings are. There are three ways to represent strings, no? Single quote, and then double quote, and then also if you want a multi-line string, you can have a triple quotes, no? Para hindi ka maglalagay ng mga new lines, explicit new lines, no? So for a string, you can concatenate two strings, no? So for example, hello space plus world, no? So you can do hello world, or you can repeat strings, no? Do some repetition using multiplication operation, no? So example, hello times 3 is hello, 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 no? And then slicing, this is so you can index a string and then you can slice it. It's very we're gonna discuss that later. It's very interesting part of the language, no? And these are the methods usually, no? Kikita natin, convert to upper, lower, replace, no? Split a string. And then booleans, so these are true or false, often used in conditional statements. And then list. Itong list, it can be anything, no? It can be different objects, no? Pero for our particular requirement, we just want yung arrays, no? So itong array is a list, no? Difference between an array and a ordinary list is that yung array is a specific type, no? Yung elements niya have the same type. For example, for integers yan, those are all integers, and the reason for that is gagamitin natin siya for mathematical operation. So matrix is just a list of lists. Okay. So tapos naman ito yung mga immutable data, no? So if you don't want your if you're creating a program tapos ayaw mo na yung program mo may gagamit ng, like for example, library mo, and then suddenly yung library na yun is trying to modify your data structure, and you don't want that, so tapos yung gagamitin mo. Ito mga dictionaries, these are data structure that are hash tables, no? So which means na when you query your dictionary, mabilis lang yung pagkuha ng value, no? So if you query a key, then you're able to get the value immediately, no? Because there's mabilis yung access niya. Kumbaga we're going to discuss this anyway later, yung tawag na time complexity is O of 1. Tapos may iba pang after dictionary is so ito yung mga samples ng dictionary, no? So dictionary looks like that, no? It looks like a JSON data structure, no? Um, Tapos ano siya? So meron ka siyang name and then well the key name and then the other key is the grade and then the value, no? And in order to print that, you just have to access the key. Tapos ito namang letter F na to, this is the F string, no? So, ibig sabihin, um, it will substitute maghahanap yung Python ng isang variable that is defined called letter X, and then we'll substitute that value dito sa F string na to. Okay, so we have update, can add a new field, can delete a field also. Dictionary, and then you can check if a field exists now before doing anything. And these are the standard operations, usually standard operations, no? Iterate over a dictionary or iterate over a key value pair for further processing. Okay. Tapos sets naman, the difference between sets and lists is that ano siya, no? It's unordered, no? Yeah. Yung list is ordered, kaya yung list meron siyang may mga index talaga yung mga elements doon, no? Whereas yung set it's not ordered, no? And later when we talk about slicing, hindi pwedeng i-slice to mga sets na to. And bawal yung duplicate. So it's very useful kapag gusto mong tingnan if a certain object is part of a set, no? So if you want to see if member ba siya ng set na yan, and then you can also do set operations like intersections, unions. Okay. Okay, so it is slicing, no? So slicing, this is a really nice feature of Python, no? Sa ibang languages, medyo very verbose, no? Especially if you're familiar with the Java language, it's very verbose. My friend ako na he really doesn't like Java because it's so verbose, no? But in Python, you can do things one-liner lang, no? And like for example, yeah, no? So that's very simple, no? Extracting a substring. So if you have a string called hello world, and then you want to extract all characters between 2, including 2, excluding 5, no? So ito yung makukuha mo. You just do it in this way, no? And then ito yung you can also index using negative numbers. So ibig sabihin, pabaliktad naman, no? So for example here, if you want to print the last 3 so it's that digits, last 3 characters, then you do this. Okay, tapos ito, this is really very nice, no? Reverse a string, napakasimple lang, no? In Python. Reverse a string, you just do a slice operation, and kung nakikita nyo, dito sa operator na to, no? Meron tayong dalawang colon, no? The first colon is pag may number dyan sa first colon, it means that's the beginning. And then sa second colon, in between naman, the first and second, pag may number dyan, that's the end of that's the range of your characters that you want to operate on. And ito namang last digit, ibig sabihin ito yung the skip, no? The skip count, no? So ibig sabihin ng for example, pag may number dyan na 2, ibig sabihin especially in this case, no? You begin at the 0 and then until the entire length of the string, but then you only print every other character. So for example, print every second character. Ito naman, reverse the string, no? Ibig sabihin, begin at 0 and up to the entire length of the string, but yung skip mo naman is from the negative kasi. So, ibig sabihin, galing sa uh, dulo. Galing sa dulo. And then you can also do this, no? You can slice using itong -3 and -1. So, third last up to the second last. So in general, so yung pinakita ko sa inyo, that's just a string, no? But you can also do slicing in general sa mga sequences, no? Like example of sequence is an array, no? Or a list. Yan. But not a set. So another syntactic sugar, it's really very nice. Python is called list comprehension, no? So sa ibang languages, in order to populate an array, no, you have to do a for loop na ano talaga, no? General for loop. Pero dito, you can just specify the loop like this expression, no? So, for example, expression, what you want to do, what the element would look like, and then the range of items that will be operated on, and if there's a condition. So let us give an example of this comprehension. So if you just want to list all numbers from 0 to 3, so for I in range 0 to 4, excluding 4. Now, if you want to create an array of even numbers only, so this is what you can do, no? So for I in range, if I is, ito ng percent na yan, that's called modular arithmetic na. Ibig sabihin na, get the remainder. No? If the remainder is 0, so ibig sabihin it's an even number, and you will get this. Tapos, this one is very useful sa Shor's algorithm, especially if you're cracking the RSA. Meron dong exponentiation, modular exponentiation. No? So, for example, here, meron tayong base number, which is number 7, and we want to exponentiate it, no, to the number I, but get the result, get the modulo, get the remainder when you divide by 15. So ito siya, no? So this one is also the same as this one here, no? Okay, so you can just take a look at the documentation of the power function. So ito yung makukuha mo. Okay. So, siyempre, type conversion. So Python automatically converts one data type to another. So explicit conversion, you have to, for example, if you want to print the number is, okay, you have a string called which has the number is, and then you add 3, no, for concatenation. But 3 is a integer, so you have to cast that to a string using this function. So you have to explicitly convert, otherwise your program will fail. Tapos, so once alam mo na yung mga data types, then the next logical thing is to study about control structures. No? Ito yung mga if then else, no, and mga for loops. Okay. So ito yung itsura ng if statement ng Python, no? So in Python, nakikita mo na wala siyang dito, no, parenthesis, and then meron siyang colon. Tapos the thing about Python also is that the space is part of the language, no? So kapag you created a program and then minsan is pagbaguhan ka, you will encounter na your program doesn't work, no? It turns out pala na you have mixed spaces and probably tabs, or you have indented in different no manner, no? So may iba 4 spaces, may iba 6 spaces, no? So magreklamo yung Python yan. So spacing is also very important, no? Okay. Tapos, so that was the if statement. Tapos ito naman is else if, no? So that's second condition, and then else. So the thing that's notable here is that you have a colon in your statement. So for loop. So this is an example of a for loop, no? So you have a variable called fruits, and that variable, which is a list, contains all of these elements, no? Apple, banana, cherry. And then if you want to for loop that, you just specify a name of a variable that will be that will take on the values of the elements here now, one at a time, no? In a loop, and then that will be your variable, and then just can print that. You can, so in this point here, we print lang siya, very simple. And then ito naman, so you can also do for loop. Ito yung usual mga for loop natin, no? Using an index, no? Running from 0 up to a certain number, excluding that number, no? So ang ginagamit naman na function na yan is range, no? So for I in range 3, ibig sabihin, ano siya, nagsisimula siya sa 0, papuntang 3, no? But excluding 3, so it will print 0, 1, 2, 3, 0, 1, 2. Okay? And then this is the while loop naman, no? Okay, so itong while loop, another way of looping, no, is while loop. Pero the standard way, of course, is the for loop. Kasi yung while loop is very easy to it's very easy to make a mistake, no? Like for example, you have to first initialize your counter or your variable outside, no? And then you have to make sure that you increment your counter inside, no? Otherwise you'll have an infinite loop, no? So, but anyway, the important thing here is that ito yung kanyang syntax, no? So napaka-simple talaga ng Python. And also, meron din siyang mga error handling facility, no? So if you if in your program, no, you foresee that there's a failure, no? So meron kang failure mode analysis, and you see that there's a possibility of failure here, no? So you do a try catch so that your program will not automatically exit, no? Be able to handle the problem gracefully. So try except. And of course, you can handle it, but sometimes if there's no error, then that's good, no? But kapag you are trying to open a file, no, inside the try block, then pag nakalimutan mo i-close yung file na yan, no, it's possible na after some time your program will exhaust all file descriptors in your operating system, no? So that's why you have to close your file in the finally block, no? So that whether it has an error or not, no, it will always close whatever resources that your program was using. And then functions, no? So functions, this is one way to make our programs modular, no, reusable, and to define a function, napakasimple lang din, no? So you use the def keyword and the name and the what you call this, the parameter of your function. in a column. So napaka-simple yung Python. So this one here is a fire and forget, no? Function, because you put something here and then you don't care what happens. It doesn't give you any return value. But you can also create functions that return ano a return a value, like for example this one here. So you use the return keyword, no? And then from there you can then use the return value as a value to a variable that you want to define. So for example here, you can capture the value returned in a variable. So you can capture the return value in a variable. For example here, I defined a variable called result, and then you add, and then we invoked our function called add, put the parameter 53, then print the result. But you can also define functions that return multiple values, no? So, for example, here we have a calculate operation. So, napakasimple lang to, no? It will return a given any values, any number A and B. It will return the sum, difference, product, and the quotient. So, all in one function na siya, no? And the thing about Python din is, so marami siyang ni-return, no? So you can also set you can also define variables that will capture all of these values. So you can unpack the return values into a separate variable. So for example here, some result, difference, product, quotient. Kasi itong calculate operation will return all of those values. Tapos ilalagay mo dito sa sa variables natin. And finally, this is the final, no? Importing modules naman, no? So nilagay ko sa pinaka kasi basic muna tayo, basic. And after that, we can talk about importing modules, no? Kasi sa importing kasi if you really want to do something useful, then you will want to use the library, no, of other people, no? Or even mga standard libraries in Python itself. So these are the basic syntax, no? So import, name the module, no? Or you can also do from module import content. So ibig sabihin, you have a module name or a library, and then you just import a certain function. Dito naman, you import the entire module, but to reference the function in that module, you have to give the module name, no? Which I'll show later, no? Tapos ito yung third, no? You import everything, but this is not a best practice, no? Kasi it's possible that when you import everything, you are going to have conflicts, no? It's possible that two modules can have might define different functions with the same name. So it will have a conflict. And this is an example, no? If you can import math, and then you can use the square root function in math. But you have to put not that square root. Now, if you are, there's another possibility, no? Just import the square root from math, and then you can just use the square root function without this prefix here. So for example here, ito squared 16, wala na yung math, no? Kasi we already specified it using like this. Okay, so actually that's the that's the overview, no? Now, tanong, why is it so simple, no? Why is it na napakasimple lang yung natin sa Python? Okay, papakita ko lang sa inyo. This is just to show you gaano kasimple yung gagamitin nating yung ating Python code, no? Kasi dito sa quantum computing, it's not the Python code, no? That's important. What's important is you understand the concept, you understand the gates, no? And understand mismo yung computation, understand the algorithm. But programming it, so simple. Like for example, this one is called the Deutsche-Joscha algorithm. Napaka-simple lang yung kanyang program. No? And this is one of the uh, important algorithms sa quantum computing kasi it's trying to solve a problem na kapag you program it, you try to solve it using a ordinary computer, no? It will take you in the worst case, no, exponential time. Pero dito sa quantum computing, you only need to create the program, the algorithm ng Deutsche Joscha, and it will only take one invocation of the function to solve your problem, no? And ito yung itsura niya, no? So, at ito yung itsura ng tinatawag na quantum gates, no? Na-mention to kanina ni Elmer. So napaka-simple lang, no? Kaya simple lang din yung binigay ko na Python introduction. There's nothing fancy here. Yeah. The fancy thing really is understanding the mathematics. Kaya itong mga programming na to, usually when you're taking or learning about quantum computing, no? Nasa huli na tong mga to eh. Okay, nasa huli na to kasi napakasimple lang talaga. So, ang mahirap is paano mo maintindihan yan, no? Daming hadamars, no? Okay, may mga control gates ka pa dito, control C na. Control na. Yan. Okay, so that's it, no? Now, I actually prepared a certain, I don't know, a quiz, no? So that all of us can participate. So I guess, Jabez, is it okay if you can give them the link? I'll stop sharing muna. No? I'll prepare my quiz. Okay, so I'm going to share my screen again. No? Paano ba mag-share dito ulit? How do I share this? Share my screen. Okay, guys, no? So the name of the game is called Kahoot, no? So you just have to use your cell phone. No? You use your cell phone. Tapos, you have to go to that link, no? For example, here, Safari. So ganito yung itsura niya, no? So let me see. Can you see this? Okay. And then, may nakikita kayong dito, may nakikita kayong number dito, no? You put your number, input your number. Tapos, yeah, that's good, no? So you can use any name like Christmas balls, no? RA, Nap-Naps, or Gabs, no? Okay. So, probably, ilan ba tayo? So, hindi kasama dito yung one quantum, no? Kasi, yung winner dito, no? We are going to give some shirt, something like this, no? So, yung magiging winner sa ating Kahoot, no? Going to give some shirt. And, so, hindi kasama yung mga one quantum. Okay. Christmas balls. Okay, so si Jabez, so hindi mo nakasama yung ano na. Okay, so can anyone help me if okay na lahat? We can start. Okay, so the coverage of this is very simple. No? It's the one which I lectured earlier, and the other one is may konting nilagay akong complex numbers, no? And yeah, I think complex numbers and ano, doon naman sa doon sa lecture ni Elmer, no. Okay, so I guess okay na tayo. Okay, so not sure if everyone's participating, but we can start na because it's almost 7 na. Okay, so let me start. So by the way, guys, no, so if you are mabilis ka sa pagsagot, no, you'll get more, and if yung sagot mo is tama, you'll get more points kesa doon sa nakasagot ng tama pero medyo mabagal, no. Now, of course, if your answer is wrong, then walang points. Okay, let's start, no. Okay, review. Quiz. Which of these is the correct variable assignment in Python? Okay. Int x equals 10, x equals 10, bar x equals 10, x assign the value 10. Great, no? So, maraming nakakuha. Okay. Very good, very good. Okay, next. Okay, so jobs, not, no? Reindeer, Sir Gabs, C sharp. So, first 5 lang, top 5 lang. No? Okay, how do you create a list in Python? Okay, alin dyan? Nice. Okay, very good. Okay. Next. Leaderboard, jobs. Okay. Number 3, what is the output of print 2 times 3? Okay. Okay, mostly got it, no? Okay, Sir Gabs na yung leader ngayon, no? Okay, how do you comment a line in Python? We had to mention to, pero it's very obvious in my code examples, no? Saan dyan yung comment ng Python? Okay, okay. So this one is the correct answer. Okay, so Gabs is still leading. What is the output of print? Hello one, no? Hello one. The correct answer is E. Ito. Great. So si Gabs pa rin is leading, no? Which keyword is used to define a function in Python? Simple. Everybody should be able to get that. Okay. So it's called def, no? Def. Okay. Mukhang constant tong mga to, ah. Okay. Which of the following is the correct way to start a loop in Python? So we have a for I. Meron dito isang for, tapos may while, tapos may loop. Okay, medyo kailangan pa natin mag-aral ng ano, no? Review ng Python, no? So ito yung ano, ito yung correct answer. And actually, 5 is also correct, no? Although the best practice is the for I, no? Okay. Oh, nag-change lang ano, nag-change lang suggested si Louie, no? Okay, tingnan natin to. How do you check the length of a list? Ako, nasabi ko ba yan? Okay, so it's length by list. Okay. Wow. Hey, XD, sino to? Okay, double points, no? How do you slice a list to get all elements except the first and the last? First and the last, no? Malin dyan. Good work, huh? So almost half, no? Sagot sa tamang sagot. Uy, ano na? So jobs now number 1, no? So, may mga bago na. Next. So what does this mean? My list, no? Slice, my list. Colon 2. What does that mean? Nice. Okay. Selects every second element starting from the first. Okay. Next. Double points. If you roll a 6-headed die, what is the probability of rolling a number greater than 4? Okay, so this is probability na. Napakasimple lang yan, no? High school yan. Very good, no? The answer is 1/3. Okay, tingnan natin kung sino yung mga, ano? Okay, may bago na. Okay, si Jess. Next. So if two events A and B are independent, what's the probability of both A and B occurring, no? I'm not sure if this was discussed by Elmer, no? Pero definitely, nasa high school to. Okay, so the answer is number 3, no? It's you multiply the two probabilities. C sharp. Constant tong mga to ah. Galing ah. Ito naman, double points. Bag contains 3 red, 2 blue balls. What's the probability of drawing a red ball? Very good, no? It's 3/5. Okay. Hindi na yata nakahabol yung iba. Okay, 14 out of 20. Double points. If you flip 2 coins, what is the probability of getting at least one head? Okay, isa lang nakakuha. 75%. Okay, singati ko sa inyo yun. Bago na ba? Oh, hindi nagbago ah. Jobs yata yung nakakuha na. Next. Okay, Euler's formula. What is Euler's formula equal to? Diyan. May mga tinuro kanina ni Elmer, no? Great, no? So 6. Got it. But 10,000 na. Next. True or false? Creator of Python programming is Guido van Possum. Yata lahat ah. False. Okay. So it's Guido van Rossum. Okay? Hindi, Possum. Oh, mukhang si Jobs yung consistent ah. 17 out of 20. Double points. If z is equal to e to the I pi, what is the value of z? You can just also pindot anywhere, no? You have a probability of 25%, no? Getting the right answer. Good. So the answer is -1, no? Wow, mga sa C sharp. Okay, this is second to the last or third to the last. Double points. What is the magnitude of a complex number 3 plus 4i? Great. So its answer is 5 now. 3, 4, 5. Triangle 3, 4, 5. Oh, may mangat si arc. Okay, I think this one is second to the last. Double points. What is the phase angle of the complex number? -1 plus I. Standard position. So the answer is 3 pi over 4, no? It's 135 degrees. Okay. So it's a battle between Nap Nap and Jobs, no? And and this is gonna be the last question, so true or false. Python dictionary is an example of hash table. True or false? Okay, answer is true. Now, sino nanalo? Third place. Sino to? Si C Sharp. Second, Jobs. First place. Galing. Nap, nap, no? So sino yan? We have to identify, no? So that we can give a shirt. And we have to get the t-shirt size as well. Okay, I'm gonna unshare my screen and back to you, Jabez.
Ayun, thank you po for that. Sir Bob, ayan, nandyan daw si Sharp, si Sir Christopher, and si Napnap, si Eugene. Ayan. Sino si Jobs? Sino ba si Jobs? Parang poser ata, baka akala
Yes.
nyo ako yun eh. Hindi, joke lang.
So
Ako
let's
si
take
Christmas
note,
Balls,
ha?
hindi ako nag-answer. Ayan, si Adriel Anthony. Ayan, okay, okay. Kala ko, ano, just kidding. Pero yeah, thank you po, Sir Bob, for that very fun game. And kahit na we had 3 hours na tuloy-tuloy, almost tuloy-tuloy, of thinking about math and programming, but you still made it um engaging for everyone. And yeah, very happy. We're all very happy na even ay, alam na daw. Ayan. Even if there weren't a lot of questions, pero based on the results of the Kahoot, you were listening. All right. Okay. At this point, next slide, please. Okay. Photo up. So yeah. We hope that you're still there and you can turn on your camera so that we can commemorate, no? And this is our last session before the year. So, you can unshare muna, Keith. Thank you. Ayan, okay. Hello, hello. Magandang gabi po. Ayan, hopefully you're well and safe. Okay, okay. Hello. Ayan, meron natang nasa labas pa po. Ayan, ingat po kayo. Thank you for your dedication. Ayan, meron nang nasa Christmas tree. And may pa Christmas light si Keith. Ayan, meron bang regalo sa ilalim dyan? Baka buksan na natin. Charot. Kidding, kidding. Ayan, nasa labas pa. Ayan. Ingat po kayo sa mga nasa labas pa. Again, yung po mga wala pa, or those that can't open their cameras, you can react na lang ng heart so that we can see or we can feel your presence. Okay? So 1, 2, 3, Keith, if you can count na rin.
Okay, in 3, 2, 1, I want you to smile. Okay. Okay, so face the camera. Let's take one more time. Okay, 3, 2, 1. Okay, thanks.
Thanks, everyone. Love the energy. Love the energy. Okay. All right. Wait. Okay. So at this point, yeah, we're nearing the end of our session, our last session for 2023, and we hope that you had a lot of fun and yeah, we were able to know more about quantum computing and yeah, get back to the basics of math, fundamentals of math and Python. Okay. So I'll be sending the attendance form. Right. Now, wait. Check ko ba? Yan. Okay, tama. And here we go. Here's the attendance form. You can answer that. And for your assignment, your homework, it will be together with the materials that will be sent on your email. Probably later tonight or tomorrow morning. Yeah, pero yeah, we won't be giving you too much pressure. Madadali lang yung mga items sa homework. So yeah, we encourage you to finish it before the holidays just so that wala na kayong isipin. And yeah, okay, all right. With that, at that point, yes, we would like to say thank you very much again for being with us for the past two sessions, and we officially conclude the session number two. You can answer the attendance form, and then afterwards, you can leave the call. Thank you po, and Merry Christmas. Ayan, Happy Holidays. Hanggang ano na, Happy New Year na rin. Yan, yung mga kailangan tumalon dyan, tumalon na rin. Hindi pa po huli ang lahat. Hindi, joke lang. See you on whenever. Kung January 6 man or January 8, see you po. Okay? Alright. Bye-bye.
Bye.
Thank you po. Again, here's the form. Okay po, linagay ko na sila sa waiting room. Message ko na lang yung form sa kanila. Thank you po.